on this computer. Okay, so today we're talking about the alternating series test. And of course, this is primarily used when you actually have an alternating series. We've already talked a little bit about alternating series. These came up when we were talking about the geometric series back in 11.2, where you have this plus minus, and depending on if the, it starts off positive, it starts off negative, notice that you can either have kind of the classic -1 raised to the nth power, or you could have, right, if you wanted to start off with, kind of the other one, being negative up front and then positive and so on and so forth, right? Then you may want to alter what power your -1 is being raised to. So you can do that with either n-1. That would be a fine way to do it. You could also do it as, alternate this or as n+1. Right, that of course would shift this over, or you could do, you could go crazy with this. You could do n+3 or something like this, or n+101, right? Any odd offsetting here will of course change it, so that way kind of the other whatever, if it was negative, your first term will be positive. If it was positive, your first term would be negative. So something like this. Once you have an alternating series, then we stand a chance of applying the alternating series test. And the alternating series test, this is interesting because it doesn't care so much about the entire series itself. It really has a lot to do with just the positive bit. So it's saying if you're interested in determining if an alternating series converges or diverges or whatnot, right, go ahead and take just the positive bits. So forget about the alternating piece. Notice that this says this -1 raised to the n-1, but it's of course true if you have this as -1 raised to the n as well. And so long as those positive bits satisfy two things, that is that they should be decreasing. Of course, they're positive bits, right? They're positive, and so you don't really have to worry about them being negative or whatnot. All of the alternating, all of the pluses and minuses and whatnot should be accounted for here. And then, so you want these things to be decreasing. So that is for all n, kind of if you plug in larger and larger terms, right, they should be getting smaller and smaller, closer to 0. And as you go off to infinity, hopefully it does approach 0 and not some other constant. And if that's the case, then the alternating series test will claim that this, your original series, the one with the alternating, actually converges. And so after that, I mean, we saw a number of examples related to this. Showcasing again, kind of looking at just the positive bits, these b sub n's. Kind of, you have to be very careful as we progress, right? We keep on calling these a sub n's and these b sub n's kind of different things for each section, it seems. So quite often a sub n is taken to be kind of our original series, the original terms. And now we're calling b sub n some other series. And it's just the positive bits. So it's like if you forget about the alternating, that's what b sub n's are for this section. And so, yeah, we saw lots of cases of how we can apply the alternating series test. Let's go ahead and take some questions. I think this is what all I really wanted to cover, from the videos. Let's see if there's any raised hands. Nope. How about in the Q&A, Yuan?
There is one which is asking, how do we know that the harmonic series is divergent? What test or method do we use to prove that?
Yeah, great. So the harmonic series being divergent was, well, we did make a proof of it in 11.2. We gave kind of the original proof for this. And then later on in 11.3, when we were talking about the integral test, we also brought up something called p-series, right? And it says that if our p, right, in our 1 over n to the p, if that power, that p is less than or equal to 1, we know that the series will diverge. So those are two different ways that we've encountered that normally the harmonic series is divergent. Jeff, I see that you have your hand raised. Go ahead.
Thank you, Professor. I just had a quick question about like the quiz tomorrow, in the sense that on chapter 7, we had one section where we honed our skills into which technique and test to use to do our integrals.
Yep.
Since we may not have that in this section, and we definitely have it before the quiz, will the questions generally be stated in a sense to state which technique or test we should be running, or will we have to figure that out?
It's possible, but not necessary, right? It's possible that they could also instead just say, here is a series, you decide what to do. Now, luckily right now, because it's 11.1 through 11.4, of course, 11.1 doesn't have anything to do with series. So that's all about just sequences. Basically, we have 3 sections. One section was, 11.2 about geometric series. Those are pretty easy to identify, right?
Agreed.
And so that one you can kind of set aside. Hopefully, right, you've just recently done a lot of your comparison web works. So of course, if any of the problems on the quiz look similar to those, right? Basically, I'm trying to hold off on the integral test as long as possible, right? Because the integral test is fairly painful, right? All those hypotheses to check. And I'm not even sure, right? I haven't looked at the quiz recently, how, it'd be, in my mind, it seems fairly difficult to make a comprehensive integral test problem, right? Because at the very end of the day, right? I mean, sure, we can make a true false, say, does this converge? And you say, yeah, true for it does, or false that it doesn't, right? But that's obviously missing a lot of the pieces there. So,
right. Even the series test seems to be a watered down version of the integral as far as the checks. We only have 2 instead of 3.
Yes. So even the, of course, 11.5 is not on there, right? So alternating series won't be on there, but yeah, we want to save integral test for last if at all possible.
Thank you.
Yep, no problem. Okay. So let's go ahead then and jump into our new stuff for today. And so the first thing that we do is, right, we can identify here the problem is alternating. And in particular, we could go ahead and rewrite this thing and really maybe isolate the alternating piece. Right now, it's kind of put up in the numerator here. But so this right here is the alternating piece. And then we need to identify our b sub n's, right? So if I went ahead and I factored out, or I take out the -1, the alternating piece, -1 raised to the nth power, then we're going to have this stuff left over. And these right here are our b sub n's. So the first thing, we have an alternating series. So alternating series test should at least be on our mind as far as a possibility. You could even imagine, right, if this was on the exam or some later quiz or whatnot, right, this is not a geometric series, right? And so really that's not, because of this darn n here, that's not in the exponent slot. So this, we couldn't use the geometric series test or anything on this, even if we wanted to. And so, okay, we're going to apply the alternating series test. And so we're looking for those 2 things. We're looking for that we have decreasing terms. And of course, we know, if I wanted to say something about why we have decreasing terms, well, we know that 2n plus 5 is increasing. Of course, we could take the derivative of this quite quickly. You get 2, right? And 2 is a positive number, so it has slope 2. It's an increasing line. And so this is increasing. So we know that the reciprocal of an increasing function is decreasing. So we have that overall, right, our b sub n's are indeed decreasing. The other thing that we need in order to apply the alternating series test is that the limit of the b sub n's, 1 over 2n plus 5, that this should go to 0 as n goes to infinity. And of course, we've dealt with much more difficult limits than this. Here we basically, as n goes to infinity, our numerator is just a constant 1, and our denominator keeps on growing and growing and growing, right? So we're going to have like a 1 over infinity sort of situation. And so this is going to be going towards 0. So those are our 2 hypotheses. Everything is met in order to apply the alternating series test. And so by the alternating series test, our series, summing from 1 to infinity of the alternating bit divided by this 2n plus 5, that this actually converges. And really quick, I just want to point out, and we did this a little bit in the video as well, right, that without this alternating piece, if I was to just think about really quick, 1 over 2n plus 5, and if I was to ask you if this thing here converges or diverges, right, if I take away the alternating piece and I just have all of the positive bits, and I say, does this thing converge or diverge? What's the answer to that? Does this bit over here converge or diverge? Ooh, I have about a 50-50. Yeah, the answer is that it diverges. So without the alternating piece, this thing diverges. I would use the limit comparison test to compare this with 1 over n, right? You can kind of see if you take away that 5 and, you can kind of forget about that 2 to some extent, right? That this is similar to 1 over n, and 1 over n diverges. Well, it's the harmonic series, or using the p-series test. And so there is something different. There's something special about having an alternating series. You do have to kind of put these in a different basket to some extent. Because here, even though we have something that's like 1 over n, because the terms are decreasing and because the limit goes to 0 by the alternating series test, you will see that this actually does converge. So again, the answer for this one right here is that it converges by the alternating series test, when if you were to forget about the alternating piece, that this thing actually diverges. This will end up having a fancy name associated with it, or fancy definition. We'll call this conditionally convergent. So that'll you'll see that later in today's lesson. Okay, before we start on the next problem, let's go ahead and take a few questions here. Gabriel, I see your hands up. What question do you have for us?
Yes, hello, Professor. I just had a question about at which n it is starting. So in this case, in this problem, it starts at n equals 1.
Mhm.
But do we have to do anything different if it started at like n equals 5, n equals 10, etc.?
Nope, that it would all work the same. And that's kind of all coming back to that theorem that I gave you in 11.2 that says so long as you don't do something silly, that your starting point really doesn't matter.
Okay,
So,
I understand. Thank you.
super. All right, let's take one more question here. Joe, you have the floor.
Professor.
Hi.
So for the alternating series test, it has 2 tests, or 2 things have to pass for it to be convergent.
Exactly. Well, really 3, because you need to also have an alternating series.
Okay.
So the
And
first,
then so if one of the tests fail, does it diverge, or is it just unknown?
it's that the alternating series test doesn't know.
Okay, so it's just undetermined.
Yes. Notice that for the alternating series test here, that the only conclusion that the alternating series test will result in is that if a bunch of things are true, then it's convergent. If one of those things is not true, it doesn't know. There is no result here that yields then it's divergent, right? It's just if these things are true, then it converges. If they're not true, doesn't know.
Okay, thank you.
Yeah, of course. It's kind of like the nth term test for divergence in that case, right? Where it's like the nth term test for divergence will tell you definitely if it diverges, but then if those conditions aren't satisfied, it's just, it doesn't know. And so it's a similar sort of deal here. Let's go ahead and try another one. Let me give you, maybe you've already been thinking about this, so I'll give you another 30 seconds or so. Of course, we see that it's an alternating series, and so we're inclined to apply the alternating series test to this. And so try to apply the alternating series test, and like it says up here, right, if the alternating series test cannot be applied, explain why. So 30 seconds. So it seems like regardless of what else you learn in Calculus 2, by the end of it, you will really know what arctangent looks like because this has come up many, many times, right? So arctangent looks something like this. and it has these asymptotes, right, at negative pi over 2 and positive pi over 2. And these, of course, correspond with the vertical asymptotes for regular old tangent. So for tangent inverse, they become horizontal asymptotes. And so there's a couple of different things that we can get from this picture here. The first is if you were to go ahead and plug in, start off at n equals 1, then n equals 2, and then n equals 3, so on and so forth. I saw in the chat that some folks said, right, that one, the fact that you need decreasing terms, right? When I look at my b sub n's are just the positive bits. That's what, this inverse tangent is doing, that these right here are actually increasing. And so at this point right here, this is enough to say that the alternating series test does not apply. So the alternating series test does not apply. Remember, in order for the alternating series test to apply, both of those conditions need to be true. So as soon as one of them is not true, you can really stop there, right? Because it can't work, right? However, some people also put in chat, I saw, that if you instead think about condition 2 first, right, and that's going to be the limit as n goes to infinity of our b sub n's, right? In this case, our b sub n's are this tangent inverse function, that this is equal to pi over 2. Remember, we have this asymptote over here that as you plug in very, very large things, this goes to pi over 2. And so, of course, the other thing that the alternating series test says that this limit should be equal to 0. Well, of course, this is not equal to 0. And so this right here is another reason why, if you just looked at this, you could also see that the alternating series test does not apply. So it doesn't meet either the first or the second condition. So there's actually 2 good reasons why the alternating series test does not work in this case. We would need to think about something else. Okay. Any questions on this one here? Any questions in the Q&A, Yuan?
One is asking if you have 1 over arctangent n, will it work?
Well, that's a fun question, right? So if you had 1 over arctangent, and let's make it alternating and all this sort of stuff, maybe from 1 to infinity. Let's throw this back to the class. Would we say that it is now decreasing, right? 1 over tangent inverse. If we were to look at our b sub n's for this new case, is this decreasing? And the answer is yes, right? And it's because tangent inverse is increasing. So its reciprocal, 1 over tangent inverse, is indeed decreasing. So yes, that works out. Excellent. And then we move on to number 2, right? Which is taking the limit as n goes to infinity of this bit right here. And already I've seen in chat, this is where the issue lies. We know that the limit of just tangent inverse is going to be pi over 2. So the limit of this is going to be 2 over pi, right? Because the reciprocal, remember, limits are quite nice when it comes to limit laws. Derivatives and stuff like this are a bit of a pain, right? If you just took the reciprocal of this, right, and tried to take the derivative, right, you would have to apply like chain rules and all that sort of stuff. But for limits back in our calculus 1 days, we learned that these things are quite nice, that literally if you just take the reciprocal of your answer, that's what your new answer is going to be. So 2 over pi, but sadly, this is still not equal to 0. So this would also fail. So this, right, the alternating series test couldn't give you any conclusion about this. Excellent. Let's take a question here. Anito, you have the floor again.
So do you know, like, if this was like on a quiz or exam, it just said evaluate or just like ask by which thing it converges or diverges by, like what would be the test that you would use, I guess?
For B here?
Yeah.
So imagine if you were to kind of forget about the alternating piece, which is what we've done here, we see that it's going eventually to pi over 2, right?
Yeah.
And so if you were to include in this alternating piece, that means that kind of the limit as n goes to infinity of everything here, tangent inverse of n, all this sort of stuff. There's going to be a bunch of terms up front, a whole lot of them, right? And because the limit's going closer and closer to pi over 2, eventually what it's going to be like, really I shouldn't say an equals here, maybe I'll put a little squiggle over there to say it's not really equals, but it's what it's going to be like, right? Is that eventually you're going to have pi over 2, then you're going to have negative pi over 2. Then you're going to have pi over 2, right? The limit itself, if you forget about the alternating piece, is just a solid pi over 2. So if you include the alternating piece, right, you're going to have something like this, where eventually, right, because it approaches, so you know it's got to get there. Maybe it takes a little bit of time, but eventually it's going to be like this, right? And then it's like this more or less forevermore. And so what? Maybe I'll throw this back at you, right? So now with this idea right here, do you have any idea about a test that we could use that would say that whether this converges or diverges?
I don't know, nth term maybe.
Yeah, exactly. So the nth term test says that eventually the items on the list would need to go to 0 if we have any hope of this thing converging. And yet here we see that it goes to either pi over 2 or negative pi over 2, right? This limit here does not exist. It can't make up its mind between pi over 2 and negative pi over 2, right? This darn alternating thing keeps on sending it back and forth, back and forth. And so the limit is definitely not 0, right? It's that it can't really agree with itself where it wants to be heading. And so since this does not exist, we know that there's no way that the series could possibly converge.
All right, for sure. Thank you. Yeah.
Yeah, no problem. So yeah, this is the answer was the nth term test. Excellent. Let's see here. Let's do another one here. Apply the alternating series test to the following to determine if they converge. And again, if it doesn't work, explain why. This is kind of a very interesting one here, right? This is kind of maybe a quite mysterious function. It's fairly complicated. It does look like an alternating series. So we have that going for us. So again, we're hoping, and we'll isolate our b sub n's here. Our dream is that one will have some decreasing, right? The b sub n's will be decreasing, which is not exactly obvious if that's true or not yet. I think maybe it's a little bit easier if we start off with number 2 here, right? That the limit as n goes to infinity of our b sub n's, so let me just go ahead and write my sine of pi divided by n, that this would need to be equal to 0. So let's think, as n gets very, very large, we're going to have pi divided by an extremely large number. So this is going to be going towards sine of 0. Sine of 0 is, of course, equal to 0. So actually, number 2 is satisfied. Now we have to think a little bit about number 1 here, right? Is this a decreasing function? And that's really hard to see. So let me go ahead. I'm going to draw just regular old sine. So I'm going to draw sine of x here. And so sine of x, right, it looks something like this. Goes on forever in all these directions and whatnot. And so let's think about if I was to plug in my first term here, right? My first term is when n is equal to 1. When n is equal to 1, we'd have sine of pi. That's going to be over here. It's halfway through the first period, right? So it makes it all the way through it after 2 pi. So after pi, this is where it intersects here. And next up, right, if I was to plug in 2 after that, we'd have pi over 2. That's going to be over here. So already, once we've plugged in 1 and 2, I claim that we're done. That this right here shows that this is not decreasing. The jump from 1 to 2, we saw a big increase, right? Here it was a height of 0. Here it's a height of 1, right? So we had this big increase. And so this is not solely decreasing. So sine of pi over n is not decreasing. So the alternating series test does not apply as written. this is a very, interesting problem here, because actually this is the only time where it makes an increase. After this, right, the next value that I would plug in would be n equals 3. And we'd have, pi over 3, which is somewhere maybe over in here. Then we'd have pi over 4, then pi over 5, pi over 6, pi over 7, pi over 8, pi over 9, right? It's going to be getting closer and closer to 0. We already saw that. And after this first little jump, this first little increase, it decreases forevermore. So although as written, the alternating series test does not apply to this case, because the alternating series test is very clear that it has to be true for all n. If you were to just do this, write this as, let's write down the n equals 1 term, and then start off our sum at n equals 2 and beyond that. So at -1 to the n, sine of pi over n. And by the way, if you were to plug in 1 into this, sine of pi over 1, so that's sine of pi, this is going to be just 0. Right, so it's going to be 0. And then here's where everything else is 2, 3, 4, 5, 6, all the way going off to infinity. Now, the alternating series test would apply to this. So without that first little term, that first little increase, if you just kind of take that piece off, then the alternating series test would work. But as written, it doesn't. So this is kind of a little clever thing. There's a kind of a very complicated statement for the alternating series test where it says basically exactly this, is that maybe it's not maybe it's not decreasing for all n, but if you rip off, kind of the first however many pieces, even if it's like 4 or 5 or 10 or even 100 pieces, if you really wanted to, so long as after a while it is decreasing forevermore, then you could apply the alternating series test by doing something clever like this. This is a little bit beyond the scope of our class for the most part, but yeah, this is just showing how sometimes if you're clever, you can kind of make things apply, right, with a little bit of extra effort. Okay, let's see. I see, Joe, your hand's up again. Did you have a question, or did you just forget to put it down from last time?
Just forgot to put it down. I'm sorry.
Oh, okay, no problem. Any questions in the Q&A, Yuan?
No.
Any comments or extra things you'd like to add to this? I saw when I was maybe writing this up here that the alternating series test doesn't apply. It seemed like you're like, yeah, kind of. It didn't look like you were terribly happy with that, when I was writing this.
I know you were saying that just
Okay, yeah.
okay, yeah, but still people is asking, shouldn't it not apply since it would decrease initially and then increase again?
Yeah, so formally how it is, then yeah, it doesn't, it technically doesn't apply with our statement of the alternating series test. But if your task was instead, figure out if this thing converges or diverges, then maybe that starts your quest to be, a little bit clever and, rewriting this. Aaron, I see you have your hand raised. Take a question from you and then we'll move on.
Hi, can you hear me?
Yeah, sure can.
All right, so for this question, in theory, it does not apply, but in actuality, it does apply, meaning sine does converge, but because it doesn't work with our theory. Okay, I'm just confused.
Yeah.
Like at what point can I just be like, okay, it converges definitely, or no, if I do this tricky thing, like at what point am I getting ahead of myself?
So really, this problem right here kind of distinguishes maybe between this first bit right here, where this is really what is maybe expected of us on homeworks, quizzes, exams, stuff like this. This is what I would expect for an answer for any of those, right? That it doesn't apply, right? As written, we do have an increase here from when you plug in 1 to then 2, right? There's this increase, so it doesn't apply, done. And then this bit down here is kind of, maybe this would be a little bit simple here, but it's kind of maybe a good starting or something like this to a project, right? That's kind of, okay, so as stated, it doesn't apply, do some clever things, and spend a half an hour or an hour, right? Because it's not, even though I just told you, hey, look here, and it does this, right? And everyone can say, oh, I see, right? But to come up with that on your own, I think that's probably something that would probably take, over an hour to come up with this clever trick. And so this is something that I would say is more on the level of a project. Does that kind of make sense?
Yeah, so basically just don't overthink. If you're spending too much time on a question, you're probably doing it incorrectly.
Yeah, that would be, I guess, especially in this case. And the other nice thing is that, at least for our exams, right, when we have many, many sections, we do have a statement of the alternating series test on our formula sheet. And so at least for the exams, that'll be quite nice. For the quiz that covers this, I think quiz 8, there's 11.5 through 11.8, so only 3 sections or whatnot. So just, for that, you need to make sure you know what it says about the decreasing and everything like that. But, when the exam times comes and there's a lot of stuff, you can always lean on to your formula sheet. And if it's not true based on what it says on the formula sheet, then it's not true, right? And that's it.
All right, thanks.
Yeah, definitely. All right, one more here. So for this one, again, same prompt. We're going to think about the alternating series test for this one. We have that, first of all, we could do a quick rewrite and really move the alternating piece off to the side. So we have our alternating piece, and then we have our b sub n's, 1 over the cube root of n to the 5th plus 3. And so again, we're going to try to show the 2 things. The first thing is that our b sub n's, this bit right here, these are decreasing. And so I'm going to go ahead and just say that the cube root of n to the 5th plus 3 is increasing. If you want to break this up and do a little bit more here, you could start off with just the inside here. N to the 5th plus 3 is certainly increasing, and the cube root is an increasing function. So this is really a composition of increasing functions, which stays increasing. So this is increasing. So the reciprocal of this is decreasing. And then number 2, if we take the limit as n goes to infinity of this bit right here, the cube root of n to the 5th plus 3, that this does indeed equal 0, right? We get 1 divided by a very, very large number eventually. And so 1 divided by infinity essentially becomes 0. And so those 2 things right here says that the alternating series test does apply. And so by the alternating series test, we have that our series here converges. And so that would be my final result. This little extra dot next to my negative sign, it almost makes it look like a plus sign. All right, there we go. All right. So this is a relatively nice one. You'll see a fair amount of stuff like this on WebWorks and very possibly, quizzes and exams and things like this. Now I'd like to get into something, formally this definition here comes up in the next section, but we've already started to play with these things earlier. And so I'd like to give you some of these sorts of problems, and you'll definitely see these in WebWork, by the way. So this now brings up the difference between absolutely convergent and conditionally convergent. So we say that a series is absolutely convergent if, when you take the absolute value of the terms, it converges. The second thing is we say that a series is conditionally convergent if the series itself converges. However, when you take those absolute values of the terms, that you actually get that series will diverge. So this right here is the definition. There'll be a nice theorem kind of related to this as well. It turns out that if you have something absolutely converging, it implies that the original series converges. And so we're going to get some more powers related to this. But for today's class, I just kind of want to get practice using this definition and checking whether or not something is absolutely convergent, conditionally convergent, or divergent. So basically now, instead of 2 buckets to put things in, whether they're convergent or divergent, we're now adding a 3rd bucket, right? We have conditionally convergent, divergent, and absolutely convergent, right? So now we have 3 buckets that we can kind of go ahead and place these things into. So let's go ahead and try this with a relatively nice one here. Usually the first place that I start is I always check for absolute convergence. I like to do that as my workflow. And so what I'm going to do first, right, for absolute convergence, which is this number 1 here, that means that when I take the absolute value of all of my terms and sum those up, we ought to get convergent. And so let's go ahead and check here, right? So if I go ahead and I take the absolute value of all of my terms, and I were to sum those up. Well, let's go ahead and simplify this down, right? So if we have the absolute value of -1 raised to the nth power, right? -1 raised to the nth power, it goes like this: -1, 1, -1, 1, -1, so on and so forth. If I was to apply the absolute value to that, right? Well, half the time when it gives out ones, the absolute value does nothing. It's already positive. And then the other half of the time, right, when we have these -1s, the absolute value takes those and makes them become ones, right? So the absolute value of this would just be a lot of ones. So this right here would just be a lot of ones. To some extent, after you do enough of these problems, right, you'll just see that the absolute values always kind of kills off this alternating piece. So it takes this interesting thing and then it just makes it 1. In the denominator, well, hopefully, you know, if things were working out, and in order to think about things like the alternating series test, right, this piece, the b sub n, should always be positive here. So let's just kind of double check. Well, we have 3n minus 1. If I was to plug in n equals 1 into this, that's where we're starting after all, we would get 3 minus 1, that's 2. And then, of course, this continues to increase, right? So after that, it would be 5. After that, it would be 8, so on and so forth, right? So this thing is already positive. So the absolute value is not doing a whole lot to this. Okay, so now I've rewritten this in terms of, right, simplifying down that absolute value. So again, we're checking if this is absolutely convergent. So now when I look at this right here, I think that this is somehow similar with 1 over n. What test formally would I apply in order to show that these things are similar, that they are related to each other? So I see some different questions. I see some answers related to a different question that I didn't ask, but is actually coming up next. When folks are saying p-series, that's not how you know that these things are necessarily related to each other, right? Formally, in order to relate these things, we would use the limit comparison test. So the limit comparison test, and I'm going to skip a few details here, right? You do have to tie their fates together, but I trust that you can do that you can show that they will both either converge or they'll both diverge. And then the next question that I asked, well, what does the simpler, you know, one do here? This is going to diverge by p-series. And I saw some people answering this question that had yet to be asked. So this thing diverges by p-series. And so the limit comparison test will say that our original one diverges, again, by the limit comparison test. So when we take the absolute value of this stuff, we have that this diverges. So this thing right here diverges. So what that means, right? Again, we were checking for absolute convergence. If this had ended up being convergent, we would have been done. And there would have been no more work to show. It would have just been absolute convergence and we could go home. But here, because it diverges, we know that at very least, it's not absolutely convergent. But still, we have to decide between these 2 buckets here, right? Should it be conditionally convergent or should it be divergent, right? And so we're just kind of work down the list now for conditionally convergent. Conditionally convergent says that when you take the absolute value of it, it diverges. That's what happened to us. And so now what we need to do is check, right? Does the original series itself, without those absolute values, converge or not? If the answer is that it diverges, right? Well, then it's just straight up divergent. But if it converges, then that means that it's going to be conditionally convergent. By the way, this one ends up being conditionally convergent. That will be our answer at the end of this. And in order to prove that, of course, we're going to use the alternating series test. So again, we're going to be checking here our original series. So again, we've already shown this part of the conditionally convergent. Now we're going to try to show this bit, right? If you just look at the regular old series, that this should converge. So, okay, let's go ahead and check this. And I claim that it will converge because of the alternating series test. But let's double check. So in order for the alternating series test to be true, well, first of all, it needs to be an alternating series. It is. So we're already 1/3 of the way there. Then we need to check, right? If we take the, I guess we need to have decreasing terms, right? Our b sub n's need to be decreasing. So I'll say that 3n minus 1 is increasing. So 1 over, right, the reciprocal of an increasing function is decreasing. The second bit is that we need to look at the limit of our b sub n's, 1 over 3n minus 1, and we should verify that this ends up being 0. This one's, fairly straightforward. As you just plug in a very large infinity, you get 1 divided by something very, very large. This is going to be going to 0. So by the alternating series test, we know that our original series here converges. And so now we have that the original thing converges. However, when we apply the absolute value to it, it diverges. And so we know that this right here, this series is called conditionally convergent. So our series is conditionally convergent. That's the overall answer that we're looking for here. Oops, erased part of my definition. All right, I'm sure there are some questions to this. So let's go ahead and take a few of those. Robbie, you have your hand up. Go for it.
Hi, Professor. I have a more abstract question.
Fun. Okay, let's do it.
So when we're analyzing these problems, why mathematically would it be interesting, or why should we care if something is absolutely convergent versus conditionally convergent?
Again, kind of what I'm going to fall back onto is a theorem that I have yet to give you, that if you have something is absolutely convergent, it will imply convergence. So that means that our original thing. So this is going to be a tool that we can use in order to prove something is convergent.
Okay.
So, and you can see that kind of with these alternating things is, even with the alternating series test, we kind of rip off the alternating piece and just look at the positive piece. This test that we're going to have here, that absolutely convergent series are convergent, essentially is formalizing this in a slightly different way. And so again, it's kind of another way to kind of forget about this alternating piece, because that's very difficult. That would stop you, right? This alternating piece, imagine if I told you to integrate -1 to the x divided by 3x minus 1, right? If you wanted to actually integrate this, you decided you want to use the integral test. Of course, for this problem, you would say maybe that's silly. But maybe there's some other problem out there that you would like to do this, right? That -1 to the x is very kind of complicated and annoying. And you'd love a formal way of getting rid of that. And right, the formal way of getting rid of that is say, well, instead of showing that this thing actually converges, let's go ahead and see if it's absolutely convergent, right? And so instead, you would get rid of the -1 raised to the n, which would get rid of this -1 raised to the x, and you would just have to integrate this thing here, and that would be much easier.
Okay, that makes sense. Thank you.
Cool. Yeah, no problem. Okay, let's maybe take one more question here. Jeff, you have the floor, and then we'll do another problem.
Thank you, Professor.
Yep.
Could you show real quickly, graphically, what those would look like in absolutely convergent versus conditionally?
Graphically.
Would they look the same? Yeah, would they look the same?
Absolutely convergent is a stronger condition than conditionally convergent. And so it will approach 0 faster. Here we've seen that this one right here is conditionally convergent. And I would like to be able to show that this bit down here is absolutely convergent.
Okay.
And so, and you can see that the difference here between these two, the main difference, and we've made some other kind of minor changes, but the main difference is that in the denominator here, this has a polynomial, a first degree polynomial, 3n minus 1, while this one right here has a second degree polynomial. And so to some extent, this is kind of playing around with the p series again, right? That p equals 1 isn't quite enough to get it full on convergent, but it is conditionally convergent. And then here, right, when you have p equals 2 for a quadratic, that this is going to be enough to be absolutely convergent.
All right. Thank you.
Yep, no problem. Okay, so let's go ahead and do this second one right here. Again, just as before, I said I always start with absolutely convergent, and then I'm going to check conditionally convergent, and then I'm going to check divergent. As I just alluded to, this one right here ends up being absolutely convergent, and so we don't have nearly as much work to show. So in order to show this, let's go ahead and sum up, take the absolute value of our terms, n equals 4 and beyond here. And when we take the absolute value of these things, well, in the top, we have this alternating piece. Again, negative 1s and 1s here. But when you take the absolute value of that, that's going to be just 1s all the way through. And then in the denominator, right, the denominator is already always positive, right? Imagine if you were to plug in 3 or 4, well, I guess, sorry, we would start at 4, plug in 4 or 5 or 6 or 7 and stuff like this, right? When you take any of those values, you square them, and then you add 3 to them, they're definitely positive. And so now we've simplified this down so that way we don't have the absolute value anymore. But still, we're checking, right, if this is absolutely convergent because we have made some alteration, right? We no longer have the alternating piece in the numerator there. And so I claim that this right here is going to be similar to this 1 over n squared by, again, the limit comparison test we'll be able to use to show this, right? Since we're out of time, I'll skip this yet again here, but please, you know, if this was a quiz or an exam or something like this, show that work, right? So I am definitely skipping a step here. I would get marked down something if I was to, you know, show this for, you know, like partial credit or whatnot on a quiz or an exam. But maybe you can trust me that we will get a good result. These are comparable. And so because this one right here converges by p series, we will know that our original one also converges. By, of course, this limit comparison test. So again, what we were able to show here is that when you take the absolute value of our series, that this converges. Therefore, it is called absolutely convergent. And now I know exactly which bin this lives in. I don't have to do any more work. I don't have to check about, you know, what happens if that absolute value wasn't there or anything like that. This is just called absolutely convergent. And this is where we end. So I'll say, so our series here, n equals 4 to infinity, negative 1 to the n plus 1 divided by n squared plus 3 is absolutely convergent. By definition. And so that's why you can just end it there. Of course, if we found out that this was divergent, then we'd have to continue and have to decide, right, is this going to be conditionally convergent or divergent, right? And so we'd have to do more work. But in this case, with this one check right here, we got lucky. And it turns out that it is absolutely convergent. And so we were done. All right. Well, that is it for today's class. Thank you so much, everyone. We'll stick around for a few minutes to take a few questions and whatnot. But yeah, good luck on your quiz tomorrow, and I'll see you guys on Wednesday.